You may have heard the news about ARP and how it's no longer in existence with IP version 6. It was such a huge part of IP version 4, but completely annihilated with version 6. In this lesson, we're going to focus on the replacement for that, specifically Neighbor Discovery Protocol. We'll also take a look at Multicast and how it operates and why it's so critical for IPv6 to work and how it works behind the scenes for you. And we'll also take a look with a protocol analyzer at duplicate address detection. Let's go. So let's make sure we're all up to speed. Between now and the last video, what I did is I went back to each of these devices and I enabled IPv6 on the interfaces so they're good to go as far as a link local address. And I've also hard-coded the MAC addresses. Router 1's MAC address is 4 zeros and then 8 ones. And host A's MAC address is 4 zeros and 8 A's. And host B's MAC address is 4 zeros and 8 B's. That way, when you see the IPv6 link local address with its UI64 format, you can realize exactly where those came from. So the one with a lot of A's in it will be host A, and the EUI64 address for host B will have a lot of B's in it, and R1 will have a lot of 1's in it. So let's begin. On R1, let's do a quick little test. Let's just go in and do a couple show commands to verify some details on R1 regarding its configuration. So we'll do a show interface FA0/1. That's this interface right here, including BIA. And we can see the hard-coded MAC address that I put in of 000, 1111, 1111. And we also can see the link local address that it has. Now that link local address, as a reminder, it created this EUI64 formatted host ID based on the MAC address, inserting FFFE, and it flipped the 7th bit. So we're good to go. What I'd like to do also is turn on some service timestamps. Timestamps are handy so that they can show us when an event is occurring. So we'll simply turn on service timestamps for debug, and I'm going to choose uptime. And that will show us the number of hours, minutes, and seconds since this device has been booted up. Now why? Because I'm going to do some debugs with you to show you what's happening behind the scenes, and I want the timestamps to help tell the story. The other thing I'm going to do is I'm going to clear any type of cached information about any type of neighbors I might have appear on R1. So I'm going to do a clear of IPv6 neighbors, which is a lot like an ARP cache. You know, in IP version 4, we had the ARP cache with layer 3 to layer 2 mapping. We have a similar functionality with neighbors that we can dynamically learn using the Neighbor Discovery Protocol. Let's go up to host A, and let's take a look at host A's link local address. So we do a if config, and I'll put Keith. I wrote a little script for this. There's the link local address for host A. So from R1, if we ping that IP address, we should be able to get a response. Now, the reality is this. When we send a ping out to a device, we have to, at layer 2 on Ethernet, we have to know what the layer 2 address is. With version 4 of IP, we'd send an ARP request, which is a broadcast going to everybody in the broadcast domain, and everybody would have to look at it, see if it was for them, and then respond. Well, with IPv6, there is no broadcast, and there is no ARP. What we're going to do instead, we're going to send out a multicast request asking for that information back from the network. Host A is going to hear it, he's going to respond, and that's what this debug I'm about to put on is going to help us with. So let's go back to a router 1. And on our router 1, we've turned on this debug of IPv6 for ND, that's Neighbor Discovery. And let's go ahead and do a ping. So I'm going to do a ping of the IP address of FE80, ::200, :AAFF, and FEAAAAA. Now that's the link local address we just saw on host A. Now it's asking me about which interface I want to use. That's always going to happen when you ping a link local address. Anything on FE80, it's going to say, well, I've got a couple of those. I need to know which interface you want to send it out of. Even if you only have one interface, it's still going to ask you which interface. So I'm going to do that ping. And as we do that ping, we have the response. Now take a look at the actual debug messages that are coming back. We have this message right here. In fact, let me let it finish a little bit. There we go. This first message is saying, okay, I didn't have any neighbor discovery information for this IP address. I'm going to move from deleted, meaning it wasn't there, to incomplete. And so then it sends out the neighbor solicitation. That's an NS. So it's sending out basically a request saying, hey, buddy, the person who has this IP address, FE80, blah, 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 I need to know what your layer 2 address is. He then, basically, he sends out the request. He receives a neighbor advertisement. So when we send out a solicitation right here, we usually get a neighbor advertisement in return. And this is basically coming back from host A. Look at the really cool A's in its IPv6 address. And then we learned in that neighbor advertisement that host A is at the layer 2 address of 0000 AAAA. So now we move our state for reachability from incomplete to reachable. Now, if you look at the timestamp on this, it's the 23-second mark here. And then we did our pings and, life was great. So we have communication back and forth. We also have a neighbor solicitation from host A asking information about us. And then we send a neighbor advertisement back. So we sent out the solicitation, host A answered, host A sent out a solicitation, we answered. And then after about 30 seconds, if we look at the timestamps, this was like 23 seconds. And at 49 seconds, it went from reachable to stale. And all that means is it's been about 25 to 35 seconds since I last heard a neighbor advertisement from that device. So I still have it in my cache. If I do a show IPv6 neighbors, it's still there, except it's going to specify stale, meaning, it's not that fresh anymore. It's only fresh for like 30 seconds. And that, my friends, is the replacement for ARP. That's the mechanism that Router 1 can figure out the layer 2 address of host A. It's by sending a neighbor solicitation. Host A sends back a neighbor advertisement back with that information. And that's the replacement for what used to be used as ARP in IPv4. Neighbor discovery is used in IPv6. So let's take a look at the play-by-play with the protocol analyzer. We have R1 who's issuing an ICMP message, and that's what neighbor discovery uses. It's ICMP, and we have different ICMP types. A 135 is a neighbor solicitation. So R1 sends out a neighbor solicitation, and he is specifying in his solicitation that his MAC address, his layer 2 address, is 0000 11111, et cetera, et cetera. We look at the layer 3 information. We take a look at the source IP address. Here's the source IP address that R1 is using. So his source address is FE80 200.11FF, which is the link local address that R1 is sourcing the ping from. So he sends out the neighbor discovery, and what happens? Well, the neighbor solicitation gets answered by a neighbor advertisement. So this is host A responding. So we take a look at the information at IPv6, the IP header. We have the source is the IPv6 address of host A, and the destination is the IPv6 address of R1. And inside of the payload, we have a beautiful neighbor advertisement, which is an ICMP type 136. And inside that, we should have the layer 2 address of host A. So that's great. Now, what have I been dancing around? I'll tell you what I've been dancing around. I'm dancing around the fact that how did our host A get that message and know it was for him in spite of the fact that R1 didn't have the layer 2 address of host A yet to do it? And the key is R1 is actually sending out that request to something called a solicited node multicast address. The magic is this. Every time we put on an IPv6 address on a device, whether it's a link local address or a global address, that host is going to join a special multicast group based on the last 24 bits of his host ID. Let me show you exactly what I'm talking about. So let's start out on host A. The objective here is to identify how host A joined some multicast group and how router 1 knew what multicast group to use to send the neighbor discovery to, or the neighbor solicitation to. So here on host A, let's take a look at some details of him. If we do a show IPv6 interface brief, we can see the link local address, and that's the IPv6 address that R1 was trying to reach. So it's FE80, and as we know, this is the EUI64 format based on his MAC address having a whole bunch of A's in it. Well, if we open the kimono a little bit further and we do a show IPv6 interface without the brief option, it's going to show us that yes, we have this link local address on the interface, but we also have joined a multicast group. Now FF, if it begins with FF, that represents a multicast group. And if we take a look at the last portion of this last 24 bits matches the link local host ID, or the last 24 bits of it. So here's the deal. Every time you have an interface that is IPv6, whether it's the link local address or a global address, it will automatically join a group that is FF02. The FF means it's multicast. We'll take a look at the rest of these bits in a later video, but it's FF02::1:FF. That's a special reserved group. And then the last 24 bits, which is these 16 bits and these 8 bits, match the last 24 bits of the interface. So, for example, if we added another IPv6 address to this device, which we'll do right now, we'll go into interface FA0/0, and we'll say IPv6 address. In fact, let's add one for this network segment right here. Let's do 2001, because that's where he is. We're adding a global address now, DB8, and we'll put in 21:111, and let's make him ::A. And we'll say that's going to be a /64 for the mask, and boom, we're done. Now, check this out. My hands will never leave my arms. A moment ago, he had joined the group FF02::1:FFAAAA because he had a host ID that ended in those 24 bits. If we do that same command again, show IPv6 interface, check this out. He has now joined another group that has the last 24 bits the same as his host ID. So right here, this all zeros and then the 1010, which is A in hexadecimal, that is what is right here as well. So every time we add an IPv6 address to an interface, we are going to go ahead and automatically join what is called the multicast solicited node multicast group for that interface. So now here's the magic. When R1 did a ping to this guy right here, to this guy's IP address, FE80 blah blah blah, when he did that ping, he actually sent out a neighbor solicitation to this multicast group right here. So if we take a look at the multicast, we go back to the trace for a moment, and this neighbor solicitation, there's the actual solicitation out to FF02::1FFAA, and then 4 more A's. So R1, based on the IP address we are trying to reach, actually sent the neighbor solicitation not to the unicast address of host A, it sent it to the multicast group, which host A joined, which is a special solicited node multicast group. And then once host A responded here, we then learned the layer 2 address, and then the echo requests and echo replies just went like clockwork. So the magic is the solicited node multicast group that we're joining. And the secret is the last 24 bits of each of your different host IDs, they are going to cause you to join a multicast group with those same last 24 bits, with the initial bits being set to FF02::, which is a lot of zeros, 1FF. All right, so let's take a look at another example of how IPv6 works behind the scenes. Let's say, hypothetically, that we wanted to send a message out to every single device. So let's say there's 400, 500 devices up here. There's only 2 physically shown, but there's more present. If we want to send a message to everybody, here is another multicast group that every device joins by default. It's FF. Again, the FF represents its multicast, meaning that very likely more than one device is listening. And the ::1 at the end is representing any IPv6 speaker. Meaning if we put a Linux box, an IBM box, a Windows box, an Apple, anything on this network that speaks IPv6, it's going to automatically join the multicast group of FF02::1. So what would happen if we tried to ping that address from R1? I'd like to demonstrate that for you right now. So let's go ahead and do the ping of the IPv6 all nodes multicast group, FF02::1. And before I do, let's just clear the IPv6 neighbors off of this router. I'm also going to go ahead and clear the IPv6 neighborships off of all the other devices to make sure it's a nice fresh shoot. And once that's done, let's go and do our ping of FF02::1. We'll specify our output interface of FA01, and we get some responses back in. Now, while those responses pour in, I've got these two devices on this network, and I also have a little Linux box that I brought up that has a link local address. It has its hardware address of 001122334455, and then it created the EUI64 formatted host ID for its link local as well. So we sent out 5 pings effectively, and that ping went out to FF02::1. That basically is a multicast group that everybody, this Unix box, this host, were all tuned into. And as a result, they processed it and said, oh, it's a ping request, and we don't know who to send it back to. So each of these 3 devices, they all did neighbor solicitations to R1 saying, hey, Mr. R1, we need to know your layer 2 information. Can you give it to us? So we have 3 neighbor solicitations done by the Unix box, this host, and this host, 3 neighbor advertisements by R1, which includes the layer 2 address of R1, and then once they all received it, they could reply to the ping requests. And that happened 5 times, responded to by each device for a total of 15 total pings. So 15 multicast replies and no errors. The replies are actually unicast replies. So let's take a look at the protocol analyzer to see what happened and verify what happened behind the scenes with this multicast ping. So here's the play-by-play behind the scenes. I've got 3 devices on our network. We have this Unix box, host A, and host B, all on this network segment, along with R1's FA01 interface. And just a moment ago, we did a ping to the multicast group FF, that's the key, it's multicast, 02::1. As we discussed, that special group is joined by every device on the network that's running IPv6. So even though we don't have a broadcast address anymore in IPv6, if we wanted to send a message out, we could send it out to FF02::1, and that would get to everybody. So it has the same effect as a broadcast on IP version 4. So let's take a look at how this plays out. If I send out this FF02::1 as a destination, how does that look, or what does it look like at layer 2? Because switches deal with layer 2 addresses, and our computers, they receive the bits and they take a look at the layer 2 addresses to see whether or not that layer 2 frame has meaning for them. In IP version 4, a broadcast had meaning for everybody, so they all had to process the packet and take a look at it. In IPv6, because all loops have joined FF02::1, they are all interested in what may be behind that frame. So what exactly is the layer 2 frame for an IPv6 address, this multicast group? And the answer is right here. Because MAC addresses on Ethernet, Ethernet is Ethernet, it has to be 48 bits in length. So for normal multicast, like this multicast group right here, the last 32 bits match the last 32 bits of the host ID that we're trying to reach. Now in multicast, they call that a group identifier. So the last 32 bits of the group identifier are going to be specified as the last 32 bits of the MAC address for the destination MAC address. We're also going to prepend that with 4 threes. So 32 bits here plus 16 bits more here is a total of 48 bits. So every device in IPv6 is listening to the MAC address or thinks it's interesting if it's 33.33.0.0.0.0.0.1 because everybody has joined this group. Okay, so great. It's an ICMP echo request. If we take a look at the details, it's an echo request from R1. Now, what do all these devices do with it? Now, here's what's going on in their minds. Oh my goodness. We just got an ICMP echo request, say these 3 devices. If we were good citizens, we would respond, but we can't. We don't know what the layer 2 address, the MAC address is of R1. We're not going to reply back to a multicast address. This packet came from FE80 : blah, 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 R1's link local address. So each of these devices are going to need to do a neighbor solicitation to figure out what is the layer 2 address of FA0/1 on R1. So we start off with this guy. So this is this MAC address right here, this FE80 address is this Unix box. So he was the first one to the party. So he sends out a neighbor solicitation. And who does he send it out to? He sends it out to the solicited node address that corresponds to R1's IP address. So if we take a look at the neighbor solicitation, it's coming from FE80 and the IPv6 address of the Unix box to the special solicited node multicast address of R1, FF02:1:FF, and the last 24 bits of the solicited node multicast address match the host. So, Keith, are you telling me that if we went to R1 right now and we did a show IPv6 interface, it would show us that R1 had joined this group and was just waiting? And the answer is yes. Let's go take a look. Over on R1, let's make a road trip over here, and we'll say show IPv6 interface, and there is his multicast group. And that's exactly the multicast group that, or this Unix box, sent to elicit the neighbor solicitation and ask R1 for that information. Now, the really cool thing is that when this Unix box made that neighbor solicitation, that was sent into the network. If we had a switch that was forwarding that to everybody because it didn't know where people lived, everybody would receive the bits, but host B and host A, because it came from this device and it's a neighbor solicitation for this specific multicast group, because they haven't joined that multicast group, they don't have to process it. They look at the layer 2 frame and say, yep, I'm not interested in that. I'm not even going to waste time on it. So we're not making everybody on the network, even if they got the frames, which we can, with switching, we can control that as well. But even if they got the frames, they wouldn't have to process them beyond looking at the layer 2 address and saying, I'm not interested. Now R1, because he's joined that multicast group, he is interested. And as a result, he sends back a neighbor advertisement, which is right here. So here's our neighbor advertisement sent back to, specifically back to this Unix box, to his link local address. Now he knows inside of that, by the way, if we open it up and we scroll up a little bit here, it's got the layer 2 address of R1, which is what we were primarily after. And as a result, now the Unix box knows how to respond back and sends his echo reply, which is right here. And then all the rest of it is unicast between the two addresses. So what have we learned about multicast groups? Here's what I want you to take away from this. If the IPv6 address starts with FF, you know it's a multicast group, that there could be more than one device who's paying attention to that group. We also identified that on a device that has an IPv6 address, it's also going to join what is called the solicited node multicast group for that, which is FF02:1:FF, and the last 24 bits are going to match the host ID for that interface that we've added to it. For normal multicast, like FF02:1, that is going to use the last 32 bits is going to match the group. So with FF02:1, the last 32 bits represent the group ID. And as we convert that into a layer 2 address, we're going to have 3333, and the last 32 bits are going to match the group ID. With the solicited node multicast address, we're going to have this string in front and only use the last 24 bits, these guys right here, to match the actual interface that the client has. So that's a really important aspect, just to keep it straight and understand why these addresses show up. Sometimes, let me chat with you for a minute. Sometimes I realize, well, I'm just going to let it happen, and good luck with everything else. As we start building on this base core of knowledge, and we start working with routing protocols and how they operate, it is going to be critical for troubleshooting and implementing to make sure you understand the basic mechanics. So in this discussion today, we've discussed neighbor discovery. And neighbor discovery is pretty simple. It's when you have a device that wants to primarily learn the layer 2 address of somebody else in that local segment. It can send out a request to the solicited node multicast group associated with that address it's looking for, and then hopefully get a neighbor advertisement as a response. With normal multicast, instead of using the last 24 bits, we use the last 32 bits. which is the group ID for the multicast group that we're trying to reach. So we could use multicast groups for all kinds of purposes. Right here, it's primarily just to demonstrate that every device is joining the multicast group of FF02::1, and every device will join a solicited node multicast group depending on the interfaces that it has IPv6 configured for. Now, the last piece of our discussion today is going to be duplicate address detection. And that is, when we did apply an IPv6 address to an interface, how did it know? How did a router know that no one else was using that IPv6 address, whether it's a link local or a global address? And the answer is duplicate address detection. And part of the secret here is that duplicate address detection involves using the solicited node multicast group. Because if R1, let's say R1 just for a moment, wanted to have a new IPv6 address put on it. Let's say we're going to put on the IPv6 address of 3333:3/64. Before R1 would start to use that, he would send out a solicited node request asking if anybody has that address in use, and he would send it to the solicited node multicast group address, and if anybody already had that address, they would respond. So let's take a look at that and also put a protocol analyzer on it just to verify what is happening. So we'll go to R1, and we're going to add a brand new IPv6 address. This will also demonstrate another important concept. When you add new IPv6 addresses, it doesn't replace the old ones. You can have lots of different IPv6 addresses on the interface at the same time, lots of different global addresses, and they'll simply be additive. So let's do a config T, and we'll go to interface FA0/1, and let's add down the IPv6 address, and we'll choose 3333:3. Now, you and I both know that's 128 bits. There's 6 groups of zeros right here in between the : I'm going to say /64. Let me pause just for a moment. I'm going to put a protocol analyzer on this exact config, and then we'll come back, we'll implement it, and we'll take a look at the protocol analyzer. So now the protocol analyzer is running. We'll press enter. And in the background, what's happening is R1 says, oh, I've just been told to use this IPv6 address. I wonder if it's in use. So it goes out and it sends a neighbor solicitation to the solicited node multicast group that would have been joined by anybody if they had this IPv6 address. So because the last 24 bits of all zeros and 3 are not in use by host A or host B or by the Unix device, which I removed a moment ago, nobody is going to have to process that because they haven't joined that group. Now, if there was a device that had the last 24 bits the same as 3 here, it would have responded and R1 would say, oh, that's in use, duplicate address detection failed, and as a result, I won't use this IP address. So let's take a moment and take a look at the protocol analyzer for the neighbor solicitation that R1 is going to make, attempting to find whether or not this address is in use by soliciting the solicited node multicast address. So here's the protocol analyzer for what we just implemented. R1 has a brand new IPv6 address of 3333:3, or he's supposed to use it. The very first thing he does is he reports in to a special multicast address, which is for MLD, Multicast Listener Discovery Protocol. And that's this destination right here. And he's basically saying, hey, this new address, 3333:3, corresponds to a multicast solicited node group that I'm now going to join. So the actual message he's sending is this. He is saying, I'm changed to exclude that multicast group. And that multicast group right here is the solicited node multicast group for the IPv6 address he's about to join. Now, it's kind of wacky. Like, why would I send a report saying I'm now going to exclude this address? Let's think about how a router or a PC deals with frames. If somebody sends a frame of data, layer 2, into a router or switch or PC, that device has to decide whether or not this is interesting. It's interesting if it's the MAC address associated on the interface, but pretty much we're going to filter everything else out. By joining a multicast group, we are going to exclude this IPv6 address from this multicast group from our filter, which means we're now going to go ahead and pay attention to it. So as a result, this change to exclude for this multicast group is sent out to any MLD listeners. That would be a device running multicast listener discovery. That's a whole topic for another video. So that's what this first packet's about. Then we send out a neighbor solicitation. Now we send the solicitation out to the solicited node multicast group that a device would have joined if it had that IPv6 address that ended in the last 24 bits with a 3 at the end. Because nobody responded, and that's the gap here. We have like less than a second, but still nobody responded to us. We are then going to go ahead and register that address. So we're sending a source packet to FF0216, and we're saying, you know what? I'm still going to exclude FF02:1 FF003. That's the multicast, solicited node multicast group that he is now joining because he's going to take the address. Now, what do you do if you have a brand new child? I remember my last daughter that was born. Her name's Hannah. She's awesome. And I was so excited. I was showing people pictures on my laptop and on my cell phone and stuff. And here's a picture of her. She's so great. Well, a router or a PC does the same thing. Once it has an IPv6 address, it wants to tell everybody about it. So here we have a neighbor advertisement. Normally, we only do neighbor advertisements if somebody is asking for it. So neighbor solicitation, hey, what's your info? Neighbor advertisement, we're giving the info. In this case, because we just got a brand new address, this is router 1 advertising from the source of its IPv6 address to the multicast group of everybody. Everybody who's speaking IPv6 has joined this group, and he's basically saying, hey, I've got this new IPv6 address in case you're interested. And that's it. And now he's up on the wire and happy, ready to go. Now, the other flip side of this is, what if somebody tried to use an IPv6 address and it was in use? What'll happen then? I say we set that up. Let's go ahead and tell host A that we want it also to try to use 3333:3. We'll do the same trace on it, and then we'll take a look at the results, which will be significantly different. Let's do that right now. So let me just close out of configuration mode here on R1. We'll make a road trip up to host A. And host A looks very, very familiar to the iOS interface. It's quite amazing, actually. So we'll go into configuration mode, interface for FA 0/0, and we'll give it the same, or try to give it the same IPv6 address that we gave over here to R1, which was 3333:3 with a 64-bit mask. So over here, we'll simply say IPv6 address, and we'll say it's going to be 3333. In fact, let's turn on debugging too. That'll be fun. We'll do debug IPv6 ND for neighbor discovery. And then we'll go ahead and put the IPv6 address on. IPv6 address 3333:3/64. I'm going to go ahead and hit the capture button right now, so we're capturing that data, which we are, and then we'll go ahead and let it go. Now, I'm going to let this finish, and it says didn't fly. Let me stop the packet capture, and we'll take a look at each of these parts. So let's take a look at the pieces. First of all, we have it adding the address. It's doing duplicate address detection to find out whether or not that's already in use. So this host is sending out a solicited node multicast destination address for anybody who would have already had that IP address. So he sends it out, and then he gets a response back. This is bad news. So that's R1 saying, yeah, I've got that address. I've joined that solicited node multicast group. You sent the request out to that group. I'm responding. And as a result, this device knows, oh, it's already in use, and it does not configure it on the interface. So host A didn't take the address because it was already in use. Let's bring in the protocol analyzer. I'll swing it in right here. And let's take a look at the pieces here, which should basically support what we just learned. So the first piece is host A said, I'm going to configure an IPv6 address, and it made a report to the MLD well-known multicast group reporting that it's going to exclude this multicast group from its filter, meaning I'm now going to start listening to frames that are destined for this solicited node multicast group based on what it thinks it's about to use. It sends out a solicitation. Now, let's take a look at this source IP address in the packet. This source IP address is the unspecified IP address. See : : That's 8 sets, 8 groupings of zeros. So we're sending out a request literally from in the IP header. It's specifying we don't have a source IP address right there. So we're sending it from the unspecified address. and it's going to the solicited node multicast group, which is the last 24 bits of which would match anybody who had those same last 24 bits. Now, the neighbor advertisement, or the neighbor solicitation went out, and because R1 had that address, he responded. This is the different part than previously. Before, we didn't get a response. Now, in milliseconds, or fractions of milliseconds, we get a response that R1 says, yeah, I've got that IP address, and look who he sent it to. Because the request came from the unspecified address, he sends back the neighbor advertisement to FF02::1, which is every IPv6 speaking device they've registered and joined that multicast group. So host A gets the message back because it was sent to the all nodes multicast group, and as a result, he says, oh goodness, I can't use that IPv6 address, and that means I don't have to join that stupid multicast group for that address if I'm not going to use it. So here's what these last two pieces are. He goes back and says, oh, I want to report in that I am going to include FF02::1, FF003 in my filter list, meaning I'm no longer going to pay attention to that multicast group because I didn't get to use that IPv6 address that corresponds to it. And he did it twice. So you could call it neurotic or just to make sure everybody got the info. But he sends that message once and then he sent it twice just to confirm to any multicast listener discovery devices that he is not going to use and doesn't want to see any of that information for that specific multicast group. So as a review with multicast, multicast starts with FF. If traffic is being sent to a specific multicast group like this, FF02::16, the last 32 bits of the layer 2 address are going to match the IPv6 address. So here we have 16 for the last 32 bits, and we're going to have that's going to match the last 32 bits here, prepended by 3333. Another multicast group, which is an exception to the rule, is the solicited node multicast group, which is FF02::1FF, and then the last 24 bits match the actual host ID. So the layer 3 to layer 2 correlation is for the solicited node multicast, it's the last 24 bits, and for general multicast, it's the last 32 bits that are going to match with the 3333 prepended, and for the solicited node 333FF, which are prepended in front. Now this video went a little longer than intended because I wanted to put all these pieces together because they're interrelated: neighbor discovery, multicast, and duplicate address detection. So let's make sure we're clear on the pieces. Neighbor discovery is the process by which two devices on the same local network can find out the layer 2 address information from each other. They do it with a neighbor solicitation. One device does a solicitation, the other one does a neighbor advertisement. It's a marriage made in heaven. The biggest part of that neighbor advertisement is going to be the layer 2 MAC address that the other side needs to forward frames on the network. The second piece is multicast. Multicast is really simple. It's not broadcast. A broadcast would be all devices. In IPv4, we had broadcasts. It was the all ones layer 2 address. In IPv6, we do not have broadcast anymore. Instead, we're going to have devices join multicast groups. Specifically, they're going to join FF02::1 if they're speaking IPv6 at all, and they're also going to join the solicited node multicast group, which is matching the last 24 bits for any IPv6 addresses that they have configured. And that includes EUI64 addresses and or link local addresses. That would all fit in. And the last piece was DAD, duplicate address detection. Understanding multicast and how that works first was critical to understanding DAD. And DAD's simple. It simply says, hey, I want to use this IPv6 address. Before I use it, I want to find out if anybody else is currently using it. So we source a packet from the unspecified address. That's : in the IP header. Why? Because we don't want to use an address as a source if it's already in use somewhere else. So we're playing it safe. We send a request out to the solicited node multicast group for a device that would already have joined that group based on having the address. If we don't get a response back, we say, great, the coast is clear. I'll go ahead and use that address. If we do get a response back, somebody says that it is in use, we back off and say, great, I'm going to just sit here for a minute. I'm not going to use that. Now, one other thing I want to share with you, which is pretty darn cool, is that these concepts that we've discussed, they apply to link local addresses, which start with FE80, and they also apply to global addresses that start with 2000 or 3000 anything. So 2XXX or 3XXX, that's the global routable addresses on the internet today. So the concept of duplicate address detection is going to actually happen multiple times. And as a review, just to put it all together, when R1 is enabled for IPv6 and has a link local address, it's going to do duplicate address detection to verify that it's not in use. When we put on an IPv6 global address, like 2001 something or 3000 something or something in the range of the global 2XXX or 3XXX, the router's also, for whatever IP address you give him, he's going to do duplicate address detection again by sending out a solicited node multicast neighbor solicitation, looking to find out if anybody has that in use already. So if we put the whole thing on a protocol analyzer, we would see duplicate address detection for a link local address. We would see duplicate address detection for the global routable addresses as well. I've enjoyed having in this video tour of neighbor discovery, multicast, and duplicate address detection. I appreciate your participation, and I'll see you in the next video.